Hello everyone, my name is Chen Zhengbo. Today I would like to present my paper, DSSA, Dual-Side Sparse Systolic Array Architecture for Accelerating Convolutional Neural Network Training. My presentation includes 5 parts: background, motivation, the architecture and design of DSSA, the evaluation and conclusion. As we all know, convolutional operations can be converted to GEMM operations. For example, convolution operations of 4 2 times 2 filter and 1 4 times 4 input can be converted to GEMM operation of a 4 times 4 matrix with a 4 times 9 matrix. Some research has pointed out that convolution is the most time-consuming operation in CAN. As a result, in our work, we focus on accelerating GMM operations rather than operations involved in CAN. With the development of AI technology, the size of neural network increases rapidly, which improves model accuracy and introduces redundancy in networks. Pruning method is a very common compression method used to reduce network size with acceptable accuracy loss. However, pruning method and the ReLU function in CAN introduces sparsity in networks, converting dense GMM operation to sparse GMM operation. In 2015, Google released a Systolic array-based AI accelerator (TPU), which makes the systolic array receive a lot of attention. Because of regularity and simplicity, systolic array is typically used to accelerate dense matrix multiplication. However, the pruning method introduces unpredictable zero distribution in neural networks, which makes it hard to accelerate sparse CNNs on systolic array. To address this issue, the academic community has proposed a number of solutions. Among these works, Sigma is the state-of-the-art systolic array-based training accelerator. Sigma's architecture is mainly composed of a distribution network, that is, the Banner's network, a reduction network, that is, the forward adding network, buffers, and multipliers. Compared to the basic systolic array, Sigma achieves significant speed up for sparse CNNs. However, we found that Sigma still has 2 issues. First, Sigma only supports one-side sparsity, which leaves potential performance gains. Secondly, Sigma bases its architecture on a systolic array with 128 times 128 cells, which may leave cells underutilized. We theoretically analyze the efficiency of some neural networks on systolic arrays with 128 times 128 and 32 times 32 cells. Results show that small-sized systolic array has higher utilization. In addition, some research in the literature has also pointed out the low cell utilization of large systolic array. Therefore, to further speed up sparse CNNs, an efficient dual-side sparsity processing architecture based on small-sized systolic array is desired. To address the issue of sigma, we propose the DSSA. We first introduce the wait and activation processing method in DSSA. We use an example to show how this method works. We can see the figure on this page. First, calculating the maximum number of non-zero elements in R rows. In the figure, K equals 4. Then compressing the R times L matrix row by row, which is compressed to an R times K matrix. Note that for rows whose number of non-zero elements is less than K, the residual elements are padded with zeros. Our proposed compressing method introduces 3 configurable parameters R, L, K. Note that our method is different from vector sparse, which is proposed in paper Sparse tensor core. Vector sparse used the abstract pruning method to set K, which is L divided by 4, while in our method, K is determined by the non-zero element distribution in R rows. To study how R and L impacts the compression ratio of our method, we conduct a sensitivity test where 2 real networks, including ResNet and CaFeNet, are used for evaluation. The workloads can be found in the table, and the results are shown in the figures. We can see that wait and activation compression ratio rises with the increase of L, while decreases with the increase of R. In our work, we use CR as our compression format. CR is firstly proposed in paper outer space, which removes column RD in CSR format and store values separately by row. Next, we describe DSSA's architecture. The overall architecture of DSSA is shown in the right figure. DSSA is mainly composed of a systolic array and 3 SRAMs, wait SRAM, input SRAM, and output SRAM, which transfer data with off-chip main memory via bus. In the systolic array, each column is called a column element, and each CE includes several processing elements, that is PE. The major PE is a major computing units in DSSA. Besides, the architecture also includes several cross-cycle reduction, that is CCR, which accumulate partial sum that belongs to the same column but being processed in different cycles, and some additional adders which are used to add up the result from different PEs. The microarchitecture of PE is shown in this figure. PE includes sparse filter, multiplication cells, sort module, precision converting module, adder tree, and corresponding controlling logic. Sparse filter achieves an M2N selection of activation data. Cells perform multiplication operation. The sort module adjusts the location of the multiply result to make them easy to accumulate in the adder tree. Precision converting module achieves data precision conversion. Either tree performs multiple partial result accumulation, which uses the Fang network in sigma and uses dedicated control logic generated by activation indices to replace the original root algorithm. We use an example to show how to map matrix multiplication to DSS's architecture. In this figure, yellow elements represent non-zero elements. Taking row 0 as an example, the non-zero values are W00, W01, W04, and W05, corresponding rows of activation matrix, including row 0, row 1, row 4, and row 5 are selected for multiplication. This yields a 4 times 2 activation matrix. In the first cycle, we calculate the first column of the 4 times 2 activation matrix, and the multiplication results are sorted according to their rank indices. As we can see, only results with index 0 and 1 are generated in cycle 0. They are written into the output as run. In cycle 1, the second column of activation is multiplied with similar procedure. Results with index 1, 2, 3 are generated. We can see that the partial results of index appear in cycle 0 and cycle 1. As activations from the same column may be processed in different cycles, cross-cycle reduction, which is performed by the CCR, is required. By now, all operations of multiplying the first row of weight matrix with activation matrix are completed. Multiplying other rows of weight matrix with activation matrix are operated in the rest of CEs in parallel. To determine the appropriate configuration, we conduct a design space exploration. As mentioned before, the compression method introduces 3 configurable parameters R, L, and K. Because weight and activation matrix are both compressed, DSSA architecture is determined by 6 parameters, including WR, WL, WK, AR, AL, and AK. According to the dependency between 6 parameters, the design space can be reduced to 3 parameters: WL, WK basic, and AL, where WK basic is a factor of WK. Although dependency analysis greatly reduces unnecessary explorations, there still exists a significant amount of parameter combinations. To reduce the explored parameter space, we limit space to 20 possible parameter combinations by utilizing the result from prior sensitivity tester. We determine two important architectures, that is local optimal and local worst. Parameters of local optional architecture are WK basic is 4, WL is 128, and AL is 512, where parameters of local worst architecture are WK basic equals 32, WL equals 512, and AL equals 32. We conduct experiments to evaluate the performance of DSSA. We implement the logic design of DSSA using Verilog in RTL, and we built a C++ based cycle accurate simulator to evaluate the speed up of DSSA. We select 9 representative networks in ResNet 50, ULV3 and SSD 300 as workloads. Weight sparsity are set to 80%, 90%, and 95%, and activation sparsity are set to 25%, 50%, and 75%. The evaluation results are shown in these two figures. The top figure shows DSS speed up over sigma, and the bottom figure shows DSS speed up over systolic array. On average, DSS with local optimal architecture delivers 13.81 x speed up over basic systolic array and 2.13 x speed up over sigma. DSS with local burst architecture achieves 9.97 x speed up over systolic array and 1.61 x speed up over sigma. The performance improvement runs with the increase of sparsity, which shows that DSSA can efficiently take the advantage of sparsity. As we mentioned before, DSSA is based on systolic array with 32 times 32 cells. To study how DSSA perform under other systolic array size, we conduct the scalability analysis. We compare DSSA sigma and systolic array under different cell sizes, including 128 times 128, 64 times 64, and 16 times 16. Under each size, we evaluate DSSA with local optimal and local burst parameter. In this table, smaller AR represents local optimal, where the larger AR represents local burst. Results show that DSSA outperforms sigma regardless of systolic array size. We evaluate DSS is overhead using DC2 in 28 AM technology with commercial cell library. DSS overhead breakdown shows that Sparse filter is the most expensive module in terms of area, and Addertree is the most power-hungry module. Compared to sigma, DSSA incurs 61.01% area and 38.5% power overhead count. These figures are reduced to 16.59% and 25.49% respectively when sparse filter is excluded as sigma did. The irregularity introduced by unstructured pruning makes it difficult to accelerate sparse CANs on systolic array. This state-of-the-art GMM accelerator sigma addresses this issue with two major issues: inability to spot dual-side sparsity and improving cell utilization at the cost of additional overhead. To this end, we propose DSSA to accelerate sparse CANs on basis of a small-sized systolic array, which naturally achieves higher cell utilization. DSSA relies on a cross-cycle reduction module to facilitate dual-side sparsity processing. Results show that DSSA delivers an average of 2.13x speedup over sigma with acceptable hardware overhead. Thank you very much.